Hello and welcome to this lecture. In this lecture, we're going to finally see the definite integral. So, in the previous lecture, towards the end, we saw this calculation of Riemann sum and we computed it as n tends to infinity, and we saw that we got a number, but then it was a lot of work. We had to really do some simplifications, a lot of algebra, use this sigma notation, move things around. It's a little bit confusing. If you get used to it, it's great, but otherwise it is a little bit confusing to do that. So, we really need techniques with which we can compute area under the curve easily, right? Find these Riemann sums, tend n to infinity, and then compute the integral easily. Okay, so for that purpose, we're going to study the definite integral. Once again, like I warned you, integration is slightly more difficult than differentiation in some sense. So you'll see the ready-made formulae will not be there, but we will see that as we go along. Okay, so let's start with the definition of the definite integral. So this definite integral I define is also called the Riemann integral. It's one type of integral, as we will see. Okay, so here's the definition. It's basically the limit of Riemann sums. Okay, so I've put all the things here so that we have a complete definition, but it's basically limit of Riemann sums. Okay, so the definite integral of a function f of x from x equals a to x equals b. This is denoted by this notation. This sort of elongated s is called an integral. So you read it as integral a to b f of x dx. Okay, integral a to b f of x dx. How do you define it? Integral a to b f of x dx is defined as the limit as n tends to infinity of the Riemann sum. Okay, what all do you need for the Riemann sum? You need the function, you need the limits, you need the number of intervals n, and then you need this vector x, right? What is this vector x? This is each sample of the function, so to speak, within this interval, right? So you have n intervals of width delta, and you pick one sample inside this xi. Okay, now there's a very important condition here in this limit. Okay, so this limit may or may not exist. First of all, right? We know that there are some sequences for which there's no limit, some sequences which have limit, etc., etc. So this limit has to exist. That's one condition. So this definite integral exists only when this limit exists. Okay, so that's one condition. And a very critical condition is this limit should become independent of the choice of xi. Whatever xi you pick within the ith interval, ith part, then this limit should be independent of that. So that is something that's crucial. I sort of illustrated it with the midpoint, left point and right point, and I showed how in the limit they were tending to the same thing, and that should happen. Only when that happens, this limit is said to exist. And if this limit exists and you can define the definite integral properly, f is said to be integrable on AB. Okay, on that interval AB. Okay, so this is the definition. It's basically limit of Riemann sums. Okay, so you make those Riemann sums, the limit as n tends to infinity, but the points where the sampling points of the Riemann sum should not matter. Okay, so it should be independent of that. Okay, now the question is, for what type of functions f will this limit exist? Okay, so that's a very reasonable question. So and the answer is actually very simple. It turns out pretty much for all functions. Okay, so that's the easy answer. Okay, pretty much for any function that might show up in practice anywhere, you will have integration possible. Okay, so that's a good thing. There's no issue with anything as far as integration is concerned, more or less. Okay, the only examples which don't have this integrable property are very strange examples. If at all you do very advanced courses on measure theory in mathematics, you'll come across those kind of examples. Otherwise, really you don't need those examples for most, almost all applications. I can't think of an application where this would play a role. Okay, so for technically the condition is as follows. So for instance, if f is continuous on AB, okay, but it need not be continuous everywhere. It can be discontinuous in a finite number of points, but it should have only these jump or removable discontinuities. It should not be discontinuity to an infinity. That kind of thing should not happen. If you have only a finite number of discontinuities, and there it can jump or it can have a removable discontinuity. Remember removable discontinuity, right? So some point where you can define the function so that it becomes continuous, right? So that kind of thing. So so this is really broad, and pretty much if you ask me, if f is bounded, pretty much any f that is bounded that you can come up with in a reasonable way, that is useful in applications, it will be integrable. So don't bother too much about it. We won't prove all these things very rigorously. It's a bit technical, and that's not needed for us at this point. So for us, for our purposes, we'll just simply assume any function which is reasonable, it's not blowing up somewhere, will have a integration possible. Okay, it will be integrable over the interval. The more interesting and important question is, how do you evaluate these integrals? We already saw just using the definition of Riemann sums, finding these things and evaluating them is really hard. I showed it to you for some x squared plus x plus 1. I mean, if you have root x or something, how do you do the integration, right? So it doesn't seem easy at all. You can go back and try the examples I gave you are very simple examples. Even there it was hard. If you have things like root x, pretty much you can't do anything. You don't know how that is working, okay? So it turns out for computing or evaluating the definite integral, there is something called the Fundamental Theorem of Calculus and the notion of antiderivatives. Okay, so this notion is extremely important, and we'll focus a lot on this. Okay, so because for us computing the integral for the practical cases is much more important than theoretical questions of existence. Okay, so we will look at this part, and here also it's a little bit tricky, as antiderivatives is a little bit tricky than derivatives. I'll point out why that is so, but it does satisfy some nice properties. But it's an interesting thing. So this fundamental theorem of calculus is very important. We'll see that in a little while. Okay, so before that, let me just explain the notation once again. It's a strange notation, this integral a to b f of x dx, and there's lots of things here. What is dx? What is a, b? What is this? Maybe it's clear, but what is this dx, right? So it's a little bit confusing. So I'm going to go through this each part of this notation and sort of say what these things are. This integral notation is sort of like an elongated S, okay, denoting summation. There is a summation involved here. That's what it denotes. Okay, a and b are limits of integration, and usually a is less than or equal to b. So the way the Riemann sum is defined, we always define it for a less than or equal to b. If a equals b, the integral becomes 0. Okay, and if a is greater than b, right? If a is greater than b, then the area under the curve is reasonable, whether a is greater than b or less than b. But then the integral becomes you have to take some care in the definition. So it turns out if a is greater than b, we'll simply define integral a to b as basically minus integral b to a f of x dx. Okay, so why we do this will become clear when you see the fundamental theorem of calculus. It is just to make things consistent with respect to that we define this, and this seems to be like a consistent way to do things. There's no major proof or anything for this. This is sort of like a definition. If a is greater than b, by convention we make it like this. Okay, so this f is the integrand. It's called the integrand, or the function that needs to be integrated. Okay, so that part is easy. X, it turns out, is nothing but a dummy variable here. Okay, so we keep writing integral a to b f of x dx. The x itself doesn't matter. It's a dummy variable, meaning you can change x to any other variable, right? Any other independent variable u like this, and then the integration remains the same. Whether you plot f of x versus x or f of u versus u, how will area under the curve change? It's not going to change, right? So this notation, you have to remember this x is just a dummy variable. Okay, it can be anything else, so that's okay. Finally, dx basically denotes the delta. Okay, so you remember that there is summation, and then there was a delta, and then you are limiting, tending in the limit for the delta becoming 0, and n was going to infinity, etc. All of that is captured by this dx, which is like an infinitesimal length. Okay, you have to think of it as a very short length. Okay, so it sort of denotes that this delta and this delta is tending to 0. So that's why we call it dx. Okay, so this notation is a little bit complicated, but a lot of people have a lot of intuition about this notation. They look at it and they understand it and all that. So it's like f of x dx, right? So if you think about a small rectangle, right, in the small width dx, you think f of x is a constant. F of x is the height of the function, right? And then dx is a small width, so the area is f of x dx. So you think of this f of x dx as f of x delta type thing. Okay, and then this summation, integration a to b, it basically sums these kind of areas, f of x dx, f of x dx, f of x dx, multiple of these f of x dx, you sum over from a to b. Okay, so that's how people sort of intuitively understand this notation. I hope this is clear to you. So this sort of brings out the summation involved, the area involved, f of x dx, and the limits a to b, and the limit of as n tending to infinity also. Okay, so that's about the notation. Now, so let's just explore this a little bit more to understand how this works. Now, integral a to b f of x dx, I've been saying it's area under the curve f of x from x equals a to x equals b. But this f of x may go negative. Like in this example curve I've shown here, this function is starting here, it's negative, and then it is going positive, and then it's going negative again. Okay. So it turns out if you do a definite integral from a to b like this, then it is basically area under the curve above the x-axis minus area under the curve sort of below the x-axis. What is area under the curve? You can say area above the curve below x-axis. Okay, so it will be basically this area minus the small area here. Okay, that's how the definite integral works. You think about the summation, right? For a small delta, you're multiplying by f. So if f goes negative, the area itself will go negative. We saw some examples of that also. Okay, so when you do the definite integral a to b, when you say area under the curve, you should know that it is signed area. It could be positive if it's above, negative it's below. If it's both positive and negative, it is the positive minus negative part. Okay, that's it's basically the overall summation. So you have to look at the positive part, subtract the negative part below it. So in terms of area, this is how it works. It's this area minus this area, because typically when we say area, we don't think of it as negative, right? But the definite integral has a negative area connotation also. So for this function, I'm going to make a little animation here, and as a and b moves, I'll show you these two areas and you'll see how this works. So let's get started and see this. So notice here. So here is maybe a very easy way to see it. So here, if you do the integration of this curve from a to b, it's going to be this area here above minus this area here. Okay, that's how it will work. Okay, so you should remember this, and you can see as the limits move, this positive and negative move here, and you can see how that worked out. Okay, so I hope this sort of brings out helps you remember how a definite integral is connected to the area. So you see here, for instance, this becomes positive, this becomes negative, this becomes positive, the small positive part and the large negative part. So you'll have an overall negative answer. Okay, so area under the curve, but it's not like positive area, it can be negative also. Okay, let's now talk about some important properties of the definite integral. So these properties help you in the evaluation. The first property is addition property. If you have the sum of two functions, the definite integral splits into the integral of the first function plus the integral of the second function. This is an easy property to prove. You can just look at the limit here, and the Riemann sum will split, and the limit will split over addition, and you will get this very easily. Okay, so under addition, the definite integral is very, very well behaved. Under scaling also, the definite integral is well behaved. Okay, so if you take a constant c multiplied by the f of x, and if you do the integration, you can move the constant around. The constant can come out, and then it's enough if you integrate what's inside and multiply by the c. Okay, so this is also very easy. Okay, again, the proof is very simple. I'm not giving these proofs. You can just do it with the Riemann sum, and you see that the c comes out of the Riemann sum. So it works out like that. Okay, so this is how it works. All right. So these two things are very, very interesting, and there's also integrability, right? F1 and F2 are integrable, F1 plus F2 is integrable, F is integrable, CF is also integrable. So all these things are true. Okay, so it turns out, unfortunately, there is no easy product rule and division rule. Okay, so that's what makes integration slightly more difficult than differentiation. If you remember, differentiation also had these kind of properties, and then it had the wonderful product rule and the quotient rule, right? If you have a product of two functions, you can easily do a differentiation. It's a simple formula. If you have a quotient of two functions also, you can do a very simple formula for differentiation. Unfortunately, there are no generic product formulae and quotient formulae for integration. Okay, so there are properties, you have to carefully do it, but there is no generic rule like a product rule or quotient rule. Okay, so but there's few other rules which are unique to integration. One such thing is called the splitting rule. Okay, if f is integrable on an interval and c is a point inside that interval, right? C is between a and b, then you can integrate from a to b by first integrating from a to c and then integrating from c to b. Okay, this is easy to see. In fact, this is true even if c is outside of the interval. Okay, so I stated it for c being inside the interval. C can be outside, even then the same result would be true, right? What will happen if c is on this side? You will go from a to c, and then plus you will say c to b, but then c to b is the same as minus b to c, right? So you integrate it from a to c, and then b is in between. You subtract the integral from b to c, you get the integral from a to b, right? So it's easy to see all these things work out. So all these things come from the area analog. It's very, very easy to understand these things. Okay, so the splitting also is very useful because f may have one form from A to C and it will have another form from C to B, right. So you can easily split it like that and integrate like this. So these three properties are nice, but like I said, you know, and the final property we will see is this bound property. F and G are integrable. You need F and G to be integrable here. I missed the G here. F and G are integrable, and f of x is less than or equal to g of x. Then the integral of f of x will be less than or equal to integral of g of x. Okay, so this is also a property that will be true. So this is useful sometimes when you want to quickly bound an integral without finding the exact value. Okay, so these properties are nice, simple, easy to prove, but still, you know, we don't have the product and the quotient rule. Okay, so that's a bit of a limiting factor, but let's see what we can do with these kind of properties. With this itself we can do a little bit. Let's see that next. Okay, so okay, before we move there, one more little property that we need is symmetry. Okay, so we've not defined this properly here. A lot of functions can be classified as having even symmetry or odd symmetry. Okay, several functions have this property, and it's a very useful property, particularly with respect to integration. Okay, what is the definition here? F is said to be even symmetric or simply even if f of minus x equal to f of x. What is f of minus x, by the way? If you have a function f of x, right? If you have a function f of x, let's say f of x is like this. Okay, so this is f of x. How will you draw f of minus x? It's simply you have to reflect f of x about the y-axis. Okay, if you do that, you get f of minus x. Okay, so it will look like this. Okay, so this will be f of minus x. Okay, you simply reflect about y-axis. Okay, so that you can easily see, right? This point is the same. If you have f of x here, like 1 here, it will go to minus 1 here, like that, right? So it will just reflect, every value here will reflect on this side. So it's just take the curve and flip it around this side. Okay, so that is f of minus x. Now what does even symmetry want to enforce? If a function has to be even symmetric, f of minus x has to be equal to f of x. Okay, I showed you an example here which is not even symmetric clearly, but if you take for instance x squared, right? X squared has a shape like this, right? So this is x squared. It's clearly even, no? In fact, any even power of x is even. Okay, x bar n for n even is an even function. Why? Because, you know, if it doesn't matter whether you put x or minus x, you get the same answer, right? So f of minus x equals f of x, and that is even function. Now odd symmetry is when f of minus x equals minus f of x. Okay, so this also will happen a lot. X power n for n odd is odd symmetric. Okay, that's an odd function, right? Because, you know, you can do, you know, f of x equals x, for instance. This is f of x equals x. Okay, and this is odd symmetric. Odd, this is even. I wrote that even there. Okay, so f of x equals minus x minus f of x minus f of minus x, sorry. So for instance, if you put x equals 0 here, what will happen? So if f is odd, if x equal to 0, you get that f of 0 is 0, right? Do you see that? F of 0 is minus f of 0. So that implies f of 0 is 0. So for an odd function, f of 0 has to be 0. Okay, so otherwise it cannot be odd. That's one condition to remember. But anyway, so this is the odd symmetry and the even symmetry. F of minus x is f of x, f of minus x is minus f of x. Okay, so but remember, there can be many functions which have neither odd symmetry nor even symmetry. Even simple functions like this, right? If you look at this function might be this function, for instance, right? F of x. If you flip it, it changes to some other function. Okay, it is neither f of x or nor f minus f of x, right? So it doesn't, it's neither odd nor even. Okay, so many functions like this will have this property. If you just generally draw, right? If you generally draw something like this, okay, if you flip it around, you won't get the same thing. Okay, the picture on the left of the y-axis and picture on the right of the y-axis will not be symmetric and the same. They can be different. Okay, most generally this is what will happen. So many more functions will look like this. So many functions may not have any symmetry, but many will do. Many in practice will do. What's interesting from an integration point of view and symmetry if f of x is even, then integral a to b f of x is the same as integral minus b to minus a f of x dx, right? You have an interval a b on the positive side, you have an interval minus b minus a on the negative side, right? So these two, the functions are exactly the same, so the area under the curve will exactly be the same. So these two integrals are the same. So in particular, if you do integral from minus a to a f of x dx, it will be 2 times integral 0 to a f of x dx. Okay, so this is a very useful property. When you have even symmetry, you don't have to bother with minus a, you can just do 2 times integral 0 to a. On the other hand, even more useful is odd symmetry. If you have odd symmetry, the integral a to b is minus integral minus b to a minus a f of x dx, right? So this is an important property, because it's, you know, positive side, negative side is minus. So when you do the integral, it should become minus of that. Okay. So what this implies is integral minus a to a f of x dx is actually 0. Okay. So this property simply means, you know, if you just put b equals 0 here, you'll see that this is going to work out as f of x dx integral minus a to, or you can see it another way also, minus a to 0 and then 0 to a. Whatever is 0 to a, the f of x is flipped on this side. So this area will cancel with this area and we'll get 0. Okay. So for any odd function, integral minus a to a f of x dx is 0. So this also is very useful. So once you verify the function is odd, you don't need to compute any definite integral, you can simply equate it to 0. Okay. Alright, so we're going to see some problems. So here is a question, you have to evaluate the definite integrals using area under the curve property. You know, we have done this before, no, the area under the curve for these kind of functions. So I'm not going to go into detail here. You simply plot this function, each of these functions, identify the triangles and the rectangles and compute the area. Okay, so the first problem is very easy. We did it for the Riemann sums and all that, and area under the curve calculations. So this is just area under the curve calculation of the definite integral. Okay. So here is another case where you can use symmetry. Okay. So notice here in each of these cases, okay, look at the first case, integral minus 1 to 1 x dx. Okay. This you can actually find very easily, you know, this is just a straight line, and minus 1 to 1, you'll see it goes off to 0. But you can also use the odd symmetry. X is an odd function, so integral minus 1 to 1 x dx will be 0. Okay. Here is another case, minus 1 to 1 x cube plus x power 5. If you actually plot, you can't compute these areas, right? We don't know how to do this yet. Okay, maybe immediately in the next lecture you will learn how to do this, but right now we don't know. So, but you can quickly identify x cube plus x power 5 is actually an odd function. Okay, you put x equals minus x, you get what? Minus x power 3 minus x power 5, which is minus of x power 3 plus x power 5. So this is an odd function. Okay, odd power, right? So it becomes an odd function. So once you have an odd function, it's really simple to see that integral minus 1 to 1 will become 0. So this guy will be 0. Okay. The last question is an even function. No, mod x is even. Okay. Whether you put x or minus x, you get the same value. So mod x is even. So integral minus 1 to 1 mod x, you can write it as 2 times integral 0 to 1 mod x, and then evaluate that integral using area under the curve property. Okay. So all these problems are easy problems, and you can see questions like this with the symmetry become really simple. Otherwise, you'll have to go run around and do some crazy computation with Riemann sums here. It won't work out very easily for you. Okay. So this will go off to 0. Okay. So that concludes this lecture. I hope you understood how this definite integral is defined as a limit of Riemann sums, and how that notation comes about, and how the properties are there, and most importantly, what properties are not there. Right? The product rule, quotient rule are simply not there for integration. So this is going to limit our ability to do integration formulae, okay, the methods for integration. But anyway, given these rules, what are the various types of formulae that are there, and where they come about, and how this fundamental theorem of calculus is very important, all that we'll see in the next lecture. Thank you.